Hello everyone. I hope that you have a nice lunch or you have a good ready for this last session. So the first speaker of the session is going to be Luis Koch, who's going to talk about agent feedback and star formation in Quasar. Thank you, Mr.
The subject of feedback and star formation are really central to the modern view of galaxy formation and evolution. It's deeply embedded in our language, in our textbooks, and certainly in all the cosmological and semi-analytical models argument. As one of the people, perhaps, who contributed to this almost religious conviction, sometimes I like to go back and revisit the data to ask where we really stand. I don't have time in 15 minutes to give a review, but I will try in some ways to give you an overview. Basic question I'd like to ask, and everyone should think about, is how can we truly test this paradigm? And what data are essential? In my mind, are three. If we're going to talk about feedback and quenching, we really need to think about the cold ISM. How much? Where is it? What are the kinematics? Star formation, its rate, its efficiency, history, its distribution, spatial distribution, and of course the star already formed, mainly the star component in terms of mass structure and morphology. There are many things that we can talk about, but in this talk I'll just focus on the code ISM and star formation. But I do want to remind you that this is non-trivial. An active galaxy, by definition, is a mixture of two energy processes, very different physics, very different scale, very different time scales. So for AGN, it's already very tough. For Quasars, it's extraordinarily tough, because by definition, AGN outshines galaxy. To remind you that prior to JWST, HST has been unable to detect host galaxies of the most numerous Quasars at HST. We tried only one, 30 orbits, to detect nothing. With JWST, we do a little bit better, and it's very good. I don't have time to discuss any of these details, except to tell you that my group in the last 10, 15 years has really focused on developing techniques to solve these fundamental problems. So how to measure the properties of the stars, very good data, very stable PSF, we need to have very good techniques. We need to know of Galfit. There's a new version called Galfit S, which is basically opening up the third dimension. In brief, let me just say that we've solved this problem. This is essentially measuring the ISM is tough. H1, you cannot go beyond redshift 0.1 currently. CO is good, it's extremely expensive, and we still don't know what is the cost of the CO factor, or we do, but it's certain it will be so for decades. There are many other methods we've invented, but today I'll focus on how to use velocity emission very efficiently for ISM. Star formation rate is much harder than you think. Most people think, oh, we'll just take the target for it. No, not really. I have to convince ourselves that we can trust the standard techniques, we invented many new ones, we calibrated old ones, and consider this problem also solved. So I'm going to apply these techniques, so just focus on one, how to use dust. Dust is very, very good. It's much easier than emissionized because it's continuum, it's broadband. And you can get the total dust mass, which basically you can quite robustly, it's related to the total gas mass by the gas to dust ratio, which is only half of free parameter. It's half of free parameter because it's not 283, plus gas ratio is literally the gas phase and liquidity, which is related to stars here in us with this relationship. So I claim you can get the total cold ISM very efficiently and very quite accurately. We applied it to several sets of observations, beginning with type 1 AGNs. It's all 87 low redshift Quasars with uniform, partial, and Spitzer observations. It was wide mass with 8 SED from 1 to 500 microns. And the basic conclusion is outlined in green, and which is that relative to normal galaxies with similar stellar mass, okay, this is a, you can see this plot again and again. This is a relative fraction of gas mass with stellar mass versus stellar mass. In the background, in green and in blue, normal star-forming galaxies. In red, the EG quasar, you can see they distributed just the same. There's no deficiency, no excess, has the right amount of ISM. And it also doesn't depend on the AGN luminosity or anything. Okay, so there's no evidence whatsoever that AGN feedback on global scales depletes the cold ISM. This is really bad news for simple quasar feedback. Maybe it happens on a smaller scale. Yes, you can always find some outflows here and there, and it's discussed. But what people care about is the global shut-off of star formation. This is what the community of Galaxy community talks about. And it's not supported by data. These are UV selected, the most active type 1 quasars. How about the type 2 quasars? Supposedly they're precursors or the brothers and sisters. We designed a companion study, 87 EG quasars observed exactly the same way, 1 to 5 months. The same result, absolutely the same. In this case, the blue is the type 1 quasars, and then the type 2 quasars. No deficiency in gas, no excess, just the right amount. No evidence for instantaneous gas secretion. Let's go back further. How about the lurks and boulars? Okay. Supposedly even more heavily experienced. This is the entire gold sample, 200 plus objects, which we can analyze in exactly the same way. And qualitatively, it's the same result. In Starburst, they have high starburst efficiency, so high selection, and many of them have X-rays, they have AGNs, but there's no difference between the AGNs and non-AGNs in different stages of the universe. In case you don't believe me, that this is the dust, we went and used ALMA, observed CO2-1, detection rate 100%. These spectra are very, very high. The noise ratio, no doubt, CO is there. The result is exactly the same. No gas efficiency. Importantly, from the line widths, we show that the CO Fisher relation is the same as normal galaxies, which is to say, kinematically, not just in amount, but also spatially, kinematically, full gas behaves the same. The spectra are really high quality. And look at this. Right? There's absolutely no high velocity wind. I'm not saying that there are no AGNs that have CO outflows, of course there are, many figures, but this is a large, unbiased sample, and look at the mass outflow rates versus AGN velocity. It's supposed to behave like this, according to these two famous papers. These are the PG quasars, they're all upper limits. Okay, where's the gas? I just told you the global integrated amount. We went for high resolution ALMA observations and resolved the gas dynamics of normal rotating disk. Okay, the one new factor is that the size is more compact. So the amount is the same, the global kinematics is the same, but they tend to be about 1 kiloparsec, 2 kiloparsecs. Whereas they're the same mass, star-forming galaxies have several kiloparsec sizes in CO. So they're more compact. Same amount, more compact, and extensive. Okay, star formation. We've developed methods to robustly measure star formation rates of quasars. In the background in gray is the normal star-forming galaxies. In blue are the gold stars, this famous main sequence. In red, EG quasars. Just visually, you can see that most of them lie on and above the main sequence. No question. In fact, they formally starburst significant fraction, because we can calculate the gas efficiency times the starburst efficiency. Okay, it's about a few times 10 to the 8 years, 200 million years. They're starburst, they're high starburst efficiencies. We have HSP pictures, all of these things. I'm discussing. I just want to tell you that you look at these images and you immediately tell they're not mergers. Many starbursts are not mergers. It's really interesting fact. Think about what that means. Okay? Alright, that's 87 objects. Now I have hundreds because we've invented other techniques. I won't talk about them later, but we can really populate large sample of AGNs, AGNs, they lie on and above the main sequence, interestingly, the offset in the main sequence of a specific star formation rate depends on m naught. See this positive relation, not a scatter. Generally, higher accretion rates, higher Hamilton ratios, higher offset in the main sequence, higher specific star formation rates. Is this evidence for positive AGN feedback? That's just a question I pose to you, and you can call it whatever you want, but there's no quenching. It's actually boosting of star formation. Okay. We have no time. Okay, so if you just plot the star formation rate and the accretion rate, you find a linear relation, and you can discuss it, but be careful. Both the star formation rate and the accretion rate depends on gas mass. The former is called the Kenny-Hutchins relation. You need to remove that to arrive at a true relationship. It's more scattered, but there seems to be a trend. Higher accretion rates, higher star formation rates, and higher star formation efficiency. Okay, so there's no evidence for star formation quenching. On the contrary, is evidence for star formation being boosted. But where is the star formation? Here we actually go down back to Mealy's observations using H alpha, IQ observations, some other technique to try to disentangle the BPD diagram so that we can derive radial profiles of star formation. Okay, which is what's shown here. Spatial result. We also have the CO, therefore we have radial profiles of star formation efficiency. You can see that in small radii, 1 to 2 kiloparsec, the star formation efficiency really goes up. So these are not only starbursts, they are nuclear starbursts. This is a summary. Very quickly, exogenous gas properties. Okay, there's a normal cold gas content. In fact, the kinematics are also normal because they obey the Tully-Fisher relation, both in H1 and in CO. Outflows are rare. I'm not saying they do not exist, but in general, like outflows are rare. The gas is more essentially concentrated. This severely challenges traditional models of AGN feedback. That's why people are revising. Now people talk about cumulative AGN feedback. That's another story. Okay, we'll have to see how do we test that. Star formation, there's no quenching. The star formation is normal or enhanced. In fact, it's so enhanced that the efficiency comports with starbursts. The star formation is centrally concentrated. It's a nuclear starburst. Maybe this indicates positive AGN feedback. We shall see. Okay? So these are the issues that I want to talk to people from this week. The LOC challenged me last night to talk about Portilla. So I just have to say, let's discuss this over the last years. Thank you very much.
Thank you, it's very nice talk. So we have some questions already, so
yeah. Okay. So no evidence of harmful later on. If you can see a large distance, you use the alpha code because you use that distance. And you need to disentangle the rotation or inertial motions directed driven by the bars, spirals, and to decouple and distinguish between this and alpha motions is key. To really is like high resolution. The only motion when you actually extremely far off from mergers, in place of this, very evidence of the power.
So I agree with you. That's why I emphasize. From the perspective of people who use AGN feedback in galaxy evolution, what they're talking about is local. They want to shut off the whole damn thing, right? Not just local in the center. So that's what I'm saying. Okay? So they want to blow away the gas. Otherwise, I don't understand how you quench things. They want to quench the galaxy. So yes, on small scales, you do see deviations. Let's be more careful. Okay? Deviations from virial motions. It is not at all clear to me that's the AGN and not the star formation, which is occurring at the same time. And sometimes the deviations actually due to bars and various streaming motions. Not your work, but they're very careless papers who say, oh, we have a little bit of blue wing, that's outflow, that indicates AGN feedback. I want to step back and talk about the entire galaxy, because that's what the galaxy information people want to see.
It's working. The speed is very high.
But most galaxies in the universe don't merge.
That's true.
So that's not a solution for galaxy evolution. It's a solution for some objects, certainly in low redshift, 3%, 5% at lowest spatial regions. So it doesn't work as a universal mechanism.
So when we talk about like positive feedback, so the distributions for star formation in the AGN, are they often like isotropic or circular, or are there ever like a ice or like bi-conpolar, like a polar distribution of star formation? You know, so if you got like a strong coupling between the AGN and galaxies, are there? I mean, I think I've seen cases where it looks like there's remote star formation along like flows that are interacting with this, but I mean, do you see cases like that?
Essentially concentrated and largely in dynamic fluid. That's what I was very precise in my language, based on polyfission relation. I'm not saying if you go zoom in, you will not have deviations, of course, but global things are quite regular. But it is more centrally concentrated. That is very interesting. That's why the star formation is also centrally concentrated. So that appears to be a requirement that's reasonable, right? You want to feel the central region and to bring everything in. Right? It's just that the accretion and star formation are drawing from the same reservoir material. So they are special in that way. Right here.
So great talk. So many questions, but I wanted to ask you. So you have talked all the time about quasars. So there could be feedback if the quasar phase is a very early phase that is just going on with the star formation. That's not what we have in mind. The Hawkins cartoon, the quasar phase is at the end, and that's what kills the galaxy. But if the quasar phase in the AGN history is very early.
Actually, that is exactly what Hawkins says in mind. Okay. I chose to highlight them because they're the most extreme example. That's where it should be happening. That's precisely where the blowout is supposed to occur. I guess the reason would be you might say, well, this doesn't happen very often in the local universe. True, most galaxies are not quasars and not starbursts, but the PG quasars is selected to be. Okay, so I think there should be analogs of what's happening in cosmic fluid. I say they should be, but in reality, I don't think they are, because the ISM is actually fundamentally different in high redshift galaxies versus low. In low redshift galaxies, co-ISM is too deep. It's a disk, which is misaligned completely with the angular momentum axis of the nucleus. I mentioned this morning. At high redshift, the ISM is 2.5, maybe 3 deep. You want to know what that means? We can talk later. Okay. Gas disks are thick, cold flows, etc. So the coupling between the AGN, no matter which direction it comes out, with the cold ISM is more 4pi. Locally, it's mostly just hitting the minor axis. That's the reason I think it doesn't have a big effect on the global gas content of the global gas.
Mine is very nice talk, and I'm going to argue on the same lines as we're arguing. But for me, the key word is feeding, not feedback. So as you said, both the AGN and star formation, they feed on the same gas that actually move pin marks to feed the AGN, and its way it can construct. So I think the word is feeding. So the result, the star formation, the max formation is not feedback from the AGN, but it's a consequence of the gas drawn to center that triggers both the star formation and the AGN.
I fully agree with you. I discussed this subject just because others insist on it. Yeah. Almost a religious conviction. But in high redshift, especially with redshift 6, and quasars are blowing themselves apart. So feedback, for example, BL quasars is much more permanent hydrogen. So clearly, for the same central engine, the surrounding is fundamentally different.
So, please, what would be one central takeaway message from your presentation? Just obviously see results. What would be the central takeaway message? And this is related to my second question. If you were teaching a class to graduate students about the quasar mode of fitment, what would you tell them?
Pay attention to your boundary conditions. In the boundary condition is intrinsically anisotropic. The outer boundary condition is also not spherically symmetric. And instead of trying to make movies with coarse resolution simulations, which is a great start, one should really focus on these very simple things. You know, this is simple geometry. Maybe not simple, but really to understand how the coefficient is swing, the outflow of the jets, which is again intrinsically anisotropic. How does it interact with the multi-phase, non-uniform ISM? Okay. This is intrinsically a local problem we need to resolve first in order to provide better recipes for the numerical large volume simulations. That's why I hope theorists really pay attention.
Okay, let's thank you. Okay, so our next talk is going to be by Herrera and Endoqui, who is going to talk about ondas, AGN-fueled in the Lockman-SpReSO today. Yes.
Okay, first of all, I apologize in advance because my English might be rusty. So, okay, I will talk about the total AGN-fueled in the Lockman-SpReSO, which is a work we've been working on in collaboration with Dr. González. Herrera is a bachelor student at the Milan. I'm currently a postdoc for me. Okay. So, this is actually, I believe, a very simple work, which is inspired by two ideas. On one hand, we know that some works have found that the AGN emission can contribute greatly to the dust, the cold dust in some galaxies. On the other hand, these cold AGN are obscure sources. So we happen to be working in two separate papers in which we are addressing these two topics separately. Okay, so the first one, we are conducting spectral energy distribution analysis for the Lockman-SpReSO survey. I will talk about this. And in the second one, we are looking for obscure and quantum sources in that same survey. So the goals of this particular study, joining these two ideas, is to study the properties of the cloud-invested Torus, the properties of their host galaxies, separated in Torus families, in particular the connection in the Starburst rate, and also whether these cold AGNs or cold are into AGN. And I'd like to make a disclaimer here because this is sort of still progress, so perhaps no sort of conclusions are. But okay, so a little bit about the sample we are using, the Lockman-SpReSO survey. which are observations of galaxies in the central 24 times 24 square minutes, observed with Osiris. So we have 1,037 hexagonals of the sources in this figure. These sources have been selected by far infrared data availability. So these are observed with Herrera. And because of that, these sources are sources with a lot amounts of dust. For some of them, we have spectra from series, and we have a nice set of photometry that we use to conduct the multi-component analysis of this series. So what we have done in this survey? First of all, as I said, the multi-component composition analysis of the series, but using Zihuagn, the code Zihuagn, and the model of the clumping models of Newborn to obtain the important parameters of the AGN-fueled. I think many of us are familiar with this model, the parameter. So these are the processes that we obtain in the SCD compositions. Just very quickly, we are interested mainly in this component here, which is actually the dusty doors of the sources. But I show you the rest of the components that we see. The AGN in orange, the dust in red, and the stars that attenuated stars in yellow, and the ionized gas in green. The number of AGN that we found in this survey are around 200. We are using here a cut of fraction AGN of 20% because some works in the literature said that using that with an AGN one, this is like a safe limit to say, okay, these are really AGN. And then, well, here I just show you the main properties of this survey. So we have the rest distribution in gray, the full SpReSO survey, in blue, the AGN posts, and we see that the distributions are very similar, especially for the stellar distribution, but in the total infrared density, we see that the AGN are slightly larger. Okay, and then the multi-component analysis composition gives us a lot of parameters, magnetic and from the Torus. So here I show you, for instance, the distribution, the overall distribution of the number of clouds that compose the Torus, the equatorial ring, the thickness, angular thickness of the Torus, the outer radii over the inner radii distribution. So we can see, here that the models in this sample prefer thick torus, large torus with a lot of clouds. Here I'm showing the distribution of the optical length, the Q parameter, and the viewing angle. This is also interesting because, as I said, in this sample, the toroidal we obtain are consistent with the type sources. So we have this data, but we notice that looking at these figures, we notice that sometimes the dots appear here, very in the center of the range. Sometimes it's shifted to the wavelengths. And sometimes it's shifted even to longer wavelengths. So this is what we think that we are looking here at the whole dust and Torus, right? So for the rest of the talk, I will separate these in families. We will call these ones as hot dusty torrent or HDT for short. These ones will be the warm dusty torrent, and these ones will be the cold dusty torrent. And I will refer just as HDT, WPT, and CDT. So how different are the properties of this torrent or the host galaxies of this torrent? Well, here I'm showing you the average SCD components in blue for 2 families. On the left hand, we have the HDT, on the right hand, the CDT. And the blue emission is the star emission, the yellow is the AGN, and the red is the cluster. What we observe here is, okay, first, the AGN emission in the CDTs contribute a lot to this part of the dust, which is where the dust of the galaxies is speaking. This is not surprising. The sample was selected here, and in the families was like this. Also, if we look at the pH emission in the hot family, we have a lot of pH with more or less defined intense features, and in the case of the CDTs, we will have much emission. And also, we can see the shape of this dust, warm dust of the galaxy is also different. What about the properties of the galaxies are now separately in families? Well, in red I show you the distributions of the HDT family, in green the warm family, and in blue the cold family. And we see that they are actually different. As we can see in redshift, the CDT family is at larger redshift, the median value, and also interesting, the total infrared distribution is different. Here I have to say, we have very few hot Torus. So that's why these histograms look a bit strange from the family, from the whole family. We have only 7 of them in the sample. So, but I think that we have like a hint, at least, that the behavior is completely different. Now these are the Torus properties, the Q distribution, inclination angle, number of clouds. Then, okay, let's pass to the next question, which is, are these CDTs in obscure sources? And here I'll show you the observed X-ray luminosity versus the infrared luminosity with some models that separate the unobscure from the obscure sources for a given result. Okay? So the color bar represents the relative to the sources, and if a source falls below or lies below the line of the model for the corresponding result, we can say that it is obscure. These are the sources that are obscure in the sample, and these are actually the CDTs. So we corroborate that these sources are in obscure galaxies. And then this character will ask, okay, but where is the star formation connection, which is the topic of the of the session. You watched it? Okay, so very quickly, this is a diagram of the star formation rate versus stellar mass. And then let's focus in the diagram, right? Because it's clear, I think. We have the WT family in these contours, the green contours, and this is the host family. We see that these sources have more star formation, right? I plotted the family here with points. Makes no sense to make a contour plots because we have only 7 sources, but then you can see the here. Okay, and these are the conclusions. So we find that there are different families of Torus in the survey. The majority of them are the gold family. The properties of the host galaxies are different. The properties of the hosts are different, and also the gold family have more total universities, transformation rate, and they are pursued. But of course, we need more data for our results. Okay, and
Thank you, Martin, for this very nice talk. So we have some questions. Okay.
Thanks. So I was wondering, you presented the distribution of parameters from your proposal. And then you use the model SCD to call the core like warm, cold, and hot. For example, a hot SCD would be a combination of parameters, like for example, a small size or optical or relatively high optical. So, what are these parameters for hot models or cold models? Will you say that?
Yeah, well, I can show you the distributions of these parameters for the different families, which is what I was showing in this class. And we can see the colors, they are color-coded. So,
for example, the hot models are indeed small, correct?
Yeah.
And do you have any information about the black hole masses? Or any information of the masses? Of the black hole masses?
I would like to work this with many things. This is still in progress. So, yeah, very interesting.
One question, for example, if CGAL allows us to modify the wholesale parameters to fit the observed losses, is there any chance that another set of parameters can fit the set but move the AGN contribution to another zone so that a galaxy that's classified as a warm Torus can move to hot Torus or to cold Torus?
Well, I use the full set of parameters, so maybe no. I would say no. But who knows?
Yeah, I'm wondering how to actually separate the surrounding galaxy stars component from the Torus component. Because we also see that the colder tori are getting larger, which these structures are connected. So I'm actually wondering how secure we can separate these two elements?
Okay, that's a very good question. Actually, that's topic of discussion, I think, in all the talks, right? This is fine. I think that since we are using acidic composition with nice data, it is estimated in perhaps the most consistent way that we can separate the from the, for instance, the dust of the galaxy. It's actually so you use the same method to separate this. Of course, maybe you're separating really the separation of the emission of the galaxy from the AGN.
Hello, I have two questions. One of them is, have you tried to fit this valve using the two-phase Torus?
No, not yet. I'm working almost exclusively with the bubble model.
And have you measured how, or what is the contribution of the flux in terms of flux for the Torus with respect to the other components?
Well, yes, because we have the total luminosity, which is what we show. So it is not moving anymore. But in this area, the LA of the oscillation models, you have X-ray versus the infrared AGN luminosity. This is actually the Torus luminosity. So yes, we separate that.
Okay. I have a question here. As an user of Solar, I have a lot of questions. But wanted to know if you have some correlations or some relations with the luminosity of the AGN, right? Because you were plotting with the far infrared luminosity, but from there, in the cold one, I am a little bit scared that we are putting lower luminosities AGN and grabbing just because the AGN only dominates in 100 microns, right? But do you have other bands that can constrain the AGN better? Because you are not using this.
Okay, we are doing the SEs from ultraviolet to the far infrared.
But you have X-ray data.
Sorry?
You have X-ray data, right?
Yes, we have the.
I think you should be using it.
Yeah.
To constrain better this part.
Yeah.
But it's unfair.
Yeah.
We can talk.
Yes, thank you.
I just want to congratulate you. This is very important. What you found is basically there's coal dust far infrared emission in excess of that predicted in the galaxy. Right? We asked one last question. The amount of far infrared from the galaxy, star formation is anchored by the short the entire sun. All emission hours. So what you've shown is that there's extra far infrared emission significantly actually being heated by the emission. That's normally disregarded. Most people Quasars look at the far infrared, oh, that's star formation. Finding star formation. My only suggestion is maybe you want to call it cold dust source. It's station scale, even though you can't see it, it shows really huge. All it means is that the ISM, which is dusty, you can see the nucleus, even at very low distances. So this is a large scale dust heating principle. This is by age. That's very important. Yeah, okay. Thank you.
Okay, so let's start the one again. who is to talk about estimating the size of the unit using the microlensing.
Hello everyone, I'm Kriti. I'm a postdoc working in Belgium with Dominic Stoops at the University of Liège and Martin at the University of Ghent. And today I'm presenting the work I've been doing for the past 2 years on trying to understand if and how we can use microlensing as a tool to estimate the size of the AGN-fueled. So, we all know that the AGN emits radiation in black electromagnetic spectrum, and this emission actually originates in different regions. And the most important thing here is that these regions are actually different spatial scales. And most of these regions are so small spatial scales that you cannot really measure them using the current technique that you have. You cannot really resolve them using also like many future techniques. So we look for different tools that can be used to estimate the size of, for example, corona, Emission, and as well as the Torus, Brooklyn region, and everything. So in this talk, I'm specifically talking about a tool which I don't think people really know about a lot, and it's still being explored. So mainly we look at lensing. So everyone knows the idea of lensing. Specifically, we are looking at quantity lens AGN. So a benefit that lensing gives you is that it will magnify the emission coming from the source. The source in this case is the AGN. So just a general description that you have the lensing galaxy, which basically modifies the left side for all the light coming from the source. The source is the quasar or an AGN first. And in the case of particular lens AGN, we actually see 4 images of the same AGN. And this is what the images look like. So you will generally have these 4 images corresponding to one AGN. And most of the time it will be either P95 or P95. But generally, the concept of lensing or the effect of lensing is asymmetric. So it does not really depend on the wavelength. So if you look at, for example, the spectrum of the different images, so for example, this source, we have the A, B, C, D images, and we have the spectrum for image C and D. If you look at the spectrum, it's just magnification or demagnification. The individual features are exactly the same. You get ratio, you get straight line corresponding to the lensing magnification because of the lensing axis. Now, this is where microlensing actually comes into the picture. So, in the case of microlensing, as the word suggests, it's a micro version of lensing. So, micro means 10 to the minus 6 times less. So, the lens itself is a microlens, so it's going to be much smaller than a full galaxy, a cluster of galaxy. Most of the time, it's just maybe a star or maybe structures in a galaxy that are very small, but they still lead to lensing. In this case, the effect will also be micro. And as well as the region that is being microlensed is again 10 to the minus 6 times smaller than the whole AGN. So, specific detail about microlensing is that this is incremental. So, this is not incremental, sorry. So, in the case of strong lensing, you don't see any effect based on wavelength, but in the case of microlensing, you can see effects based on wavelength. So, in this case, we have another spectrum for 2 images based on the position. But if you see, you look at the spectra, you take a flux ratio, and at certain wavelengths, you can actually see different features. Basically, the flux ratio is not constant. This is such a signature of microlensing. Now, in the case of AGN, this is extremely useful because, as I said, AGN, you have multiple wavelength emission coming from different scales. So we have the extremes coming from the smallest region to most compact region, and this would be most microlensed towards the smallest. And this has already been used in literature. Microlensing has been used to estimate the size of the X-ray corona.
to be microlensed, and you can actually get the size of the disk as well using microlensing. And this has also been giving us results about the size of the proton region, and most recently about the size of the submillimeter corona that has been estimated using microlensing. So now, what I am interested in is looking at the torus. Basically, the innermost torus, to see if microlensing can be used to estimate the size of the torus, or maybe if the torus can be small enough to be microlensed, because it really depends on the size. So, studies have already shown that the torus emits at different units based on the temperature and then the how far it is from the central region. So, for example, we have observational studies that show that as you go to higher wavelengths, also the size of the torus increases. Or basically, you get higher wavelength emission coming from extended torus. This is also seen in simulations where I've shown the 1 micron, 10 micron, and 100 micron emission for and based on the scale, you can see that the 1 micron is really concentrated in compact region, whereas the highest wavelengths are coming from more extended region. So we already know that the torus has different wavelength emission coming based on the size of the torus. Now, some simulated studies have been done. So this is based on negative transfer slot models. This was done by JWST back in 2012, and he basically made a torus model, both smooth and clumpy, to look at if the torus can be microlensed and at what wavelength can be microlensed. So we have the models for 1 micron for the 2.3 micron emission, 4.6 and 9.7, and what he showed in the top plot is 4 different colors. They are showing how much magnification you can expect, and as you can see, it changes with wavelength. So the shortest wavelength, which corresponds to the smallest size, has the maximum magnification, and the largest wavelength has the least magnification. And if you look at this in terms of the size of the torus, you can see that as you go to the smallest wavelength, you see a really large increase in the magnification. So this should be visible in observation as well, and this is what we are trying to do. So the main aim of the work is to see if we can use microlensing to get the size of the torus, mainly the most compact hotness torus. So for this, we use the sample of lens AGN. So the first step is to collect multi-band data for this lens AGN, because we actually have many discovered lens AGN, but we don't really have a combined study with multi-band data of training their physical properties. So that was the first step, to compile all the multi-band data and characterize the physical properties, and then to look for deviations in the infrared plus ratio between the different images and see if we can observationally find traces of microlensing. And then if we do, we wanted to see if we can find a relation with the region properties so we can predict microlensing, and then use it to estimate the size of the torus. So the sample consists of 27 AGN up to 3.2 lens AGN. For all these sources, we have JWST video observations in at least 4 bands, as shown here. And then I looked up the terminal online, and we had X-ray spectra for all these lens AGN. So this was extracted from the terminal online. And then also I combined the optical UV photometry data from various different ground-based and space-based telescopes, and also spectroscopy wherever it was available in the optical UV. I'm going to quickly go through how I got the physical properties. This is what we generally do for AGN. So I've tried doing the same for lens AGN. It's just a flowchart, but if you want to know the details, we can go over it later. So we start with the X-ray spectra. We create the X-ray spectra using a simple formula along with the function. So this gives you an estimate of the X-ray emission coming from the lens AGN. Next is the optical UV photometry, which is done using a vector profile, and you pick all the 4 images and get an estimate of the flux in UV. And next, also we have the spectroscopy. So we did pick available emission lines, mostly MG2 and C4, to get an idea of the full width of maximum. And we combine the spectroscopy and the X-ray and the volumetric luminosity consists primarily of the X-ray emission coming from corona and the UV optical emission coming from this. So this gives you the total appreciation luminosity of the lens AGN, and the optical UV spectroscopy gives us an estimate of the visual background mass, and combining these two gives us the emission ratio. So we get an estimate of these three main physical properties of the lens AGN. Next, we look at the related flux ratios. So this comes from for the 4 bands that are shown from JWST. So what I'm showing here on the x-axis, we have the wavelength. The 4 points correspond to the 4 bands in memory, and on the x-axis, we have the flux ratios between different lens images. As you can see, so A, B, C, D are the 4 lens images, and the flux ratios are shown in black, blue, and yellow. And what we want to look here is how these flux ratios change. Because as I told you, it's just strong lensing, it should be constant because strong lensing is ignorant. But if you actually see these changing, then microlensing is playing a role. And specifically in these cases, I'm just showing 3 of them out of the 27, the ones that show the largest variation. But you can see that as we go to shorter wavelength, there's a dramatic increase or dramatic variation basically in the mid-infrared flux ratio. It shows that the smallest, most compact region of the torus is being microlensed. And next we wanted to see that if somehow we can predict this microlensing based on the physical properties of the lens AGN. So this was here I checked the volumetric luminosity, the relation to the volumetric luminosity. So we are basically showing the flux ratio, but in terms of differences in magnitude with respect to the volumetric luminosity. The horizontal line corresponds to the uncertainty line. So anything above this is not due to systematic or modeling uncertainties. Anything above this is actually due to physical reasons. There has to be a reason for why this should be so large. So if you look at the sources that are actually above this line, most of these sources are below volumetric luminosity of 10^46, and this shows that the sources with low volumetric luminosities have AGN that could actually be microlensed. So the AGN the hottest one, is small enough to be microlensed. And if you look at these two sources that are higher luminosities, so the torus cannot be very small, but the torus size actually correlates with the luminosity. So what is going on with these two sources? Why do we have such large variations in the flux ratio? So for this, I actually plotted it against the redshift, and you can clearly see that these two sources are the highly pressure sources as well. So in this case, when we look at the literature, we are actually having some contribution from the continuum, from the disk. And as I told you, the optical disk is actually smaller, so there are more chances for the optical disk to be microlensed. So that's why we are seeing this variation, large variation, mainly because of the contribution from the disk. But if we look at pure variation to the mid-infrared, then the constant microlensing in the AGN, microlensing of the torus in the AGN, that would really be sources with volumetric luminosity below 46. So this leads us to the main conclusions that we do have mid-infrared fluctuations that can vary in quasars. So that shows that microlensing of the hot dust forest is possible. And if you want to look for sources that would have this microlensing of the hot dust forest, it would be sources with luminosity less than 46 pounds per second. The next step, what I'm working on, is first of all to quantify how much of the contribution from the accretion disk could contaminate this. And then, most importantly, doing a multivariate analysis for one of the most important parameter systems that we have. Because the closest lens AGN that we have near-infrared, mid-infrared, X-ray, optical UV, optical infrared. So the plan is to use this technique, microlensing, to estimate the size of the torus. So this is still work in progress. And hopefully we can use microlensing to estimate the size of the hardest torus for this AGN, and then maybe more in the future. And yes, thank you. Just a movie recommendation. So this movie, according to me, represents the Indian culture and traditional heritage in a very good way. And also it has drama, thriller, direction, also using the color that you know from Indian cinema. So something like that. Thank you.
Thank you for this. So we have some time for questions.
Okay, so I have one question. So do you have an estimation of the size that you expect to get from this analysis for the sample?
So we are doing it for this flow. So this lens agent, this is the closest one that I was talking about, and it has perfect size. The luminosity is perfect; it's very low relative to the limit that we have, and it also has the range of the torus to the Einstein, which is 9. Because generally we have a limit of the ratio to be 10. Less than 10, we can expect the torus to be microlensed. And based on the luminosity, we actually get an estimate of around 0.67 parsecs for the torus. So, but we would still like to. So this is just based on the optical UV and the mid-infrared, but we do have near spec data for this. So I really want to confirm that we don't have any contamination from the optical disk. So after that, this would be the next step publication.
For clarification, I'm not an expert on lensing. Why is microlensing not a? Is that a theoretical statement or based on the data structure that you showed?
So it is based on also the equations. So basically, I'm also not an expert on lensing. So what I know, so microlensing is because the structures that are causing microlensing, they are much smaller. So when they deflect the light, so they do not deflect the light of the entire AGN because the AGN is much bigger than the lens. So they are deflecting light only from specific regions. So it really depends on the size of the region. And in the case of AGN, since the multi-wavelength emission is from different regions, different physical scales, so that's why the X-ray is coming from the smallest scale, so it will be most microlensed. And the optical UV of the IR is coming from a larger scale, so that is why it will be less microlensed. So it's really specific to AGN that we see this effect. If it's
the difference that you showed was the narrowing component of the emission line.
yes.
Your structure was taken and goes to 2 different position angles.
Yes, so the 2 different position angles corresponding to 2 different images. So the slit was corresponding to 2 different images, and you see that one image is microlensed and the other is not, because it really depends on the position of the AGN on the distance.
Thank you.
Okay, so we have next one from that.
Thank you really for this last one. Just wanted to understand, based on that position memory issue, what is the impact of differential kinetic aberration? It's very important to understand that slowly galactic could have effect of wavelength dependence along the spectrum. Does that impact your observations when you're looking at the imaging?
So when you look at the different, like if you're looking for the non-achromatic effects in the fluxes, so microlensing is one of the reasons that we could see this effect. There's anyways, there could still be effects, for example, differential dust extension as well, that could play a role. And but the difference is the effect of microlensing is the strongest. So when you are also looking at different position angles, they correct it for the expected difference in the dust extinction in the line of sight as well. And then they still see a difference in the flux ratios. And then the most probable reason would be microlensing.
Okay, so let's ask Kriti and please talk. Our next speaker is Thaisa. He's going to talk about the Starburst AGN connection and the history of the universe.
Hello, everybody. I'm very happy to be here. Thank you, Maya, for the organization of this nice meeting in this beautiful location. And I'm going to talk about the AGN Starburst connection along the history of the universe. And this is a work in collaboration with our group, AGN-fueled spectroscopy group, where we have been doing AGN feeding via interactions, inflows, AGI feedback via outflows, and also stellar populations. And today I'm going to talk more about stellar populations. The motivation and summary of my talk is that, well, I'm here with reminding everybody that the Starburst AGN connection, in my knowledge, began with the languages and ideas about the target in the 80s and 90s. And they spent a long time here in Mexico doing this work as well. And I also did with in collaboration with C. Fernandes, also Gonzalo Delgado, in the 90s and 2000, some previous work on this connection. Okay? And there is this work that Ismael mentioned in his first talk, the rate of transformation down in 16. So I'm going to talk about the observations of AGN-free. I work with about cold molecular gas in the nuclear capacity of AGN, and simple look at this result there. And then I'm going to mark that this accumulated gas in the part of the capacity will increase the transmission rate. And then I'm going to talk about observation of non-stellar population and recent transformation behaviors. And mostly near, but I will start the linear results from our region. Okay, this is just to remind people of our group. Maybe key players here are going to be Giorgia Peluso, and several students and collaborators. So beginning with the feeding of AGN in this review that I wrote together with Juan in 2019, we reviewed the processes of the feeding of AGN on different scales, beginning the extragalactic scales where we find an instance of mergers that is and then inside the galaxies, there are some recent indications of inflows along bars. And in the inner to the parsec, we have been finding in many papers inflows along nuclear structures. But a key result of these studies is that the mass inflow rates that we estimate in these inflows are larger than the black hole emission rates, and orders of magnitude larger. So this means that you have accumulation of gas within the inner parsec in this galaxy. And so we have seen, for example, molecular gas accumulated in the parsec of nearby AGN, a work led by Bruno and Oliveira, where we find that the molecular gas is at the base of outflows. These red things, contours, are due to outflows seen in the optical. So these three are more obvious that you get the outflow perpendicular to the molecular gas that is in gray. Okay, so we are concluding that the cold molecular gas is accumulating, is feeding the AGN, forming the circle of this that Garcia is the expert in the gas calculations. And also we see signatures of feedback in the sense that there are some disturbances in the molecular gas surrounding, in the region surrounding the outflow. And then results from the stellar formation. Rogério. So we have been doing spectral synthesis in the optical and in the near infrared. So as I said, accumulated gas in the image opacity will be fuel for supernovae star formation. And we did some recent work with the manga data cubes. And we see in the image opacity here is, the AGN of galaxies, and we compare it the stellar equation obtained from the spectral synthesis. So the spectral synthesis, you synthesize the spectrum. I don't have time to explain too much the spectral synthesis, but we synthesize using templates of different age and ethnicities. So you can synthesize and see the proportion X here of stars of certain age and certain ethnicities. And one main result that's simplified in one case here is that we see excess of young to intermediate age stars in AGN when compared with a single proto galaxy. In this case, in the manga sample, it's about 300 AGN versus about 500 proto galaxies. So we see an excess of young to intermediate age in optical spectra in the outfield spectroscopy manga sample. And another study using spectra in the near infrared. So this is the synthesis. And the result here, we also find the excess of intermediate age stars. And I would like to highlight here in the near infrared, we find younger median age for the AGN and compared to non-AGN. The AGN are the blue, non-AGN are the red. And then we find like 4.5 years for the AGN as a median age and 7 to 8 years for the neutral galaxies. And more recent work is the calculation of star formation rate. That I think Luis mentioned that you cannot obtain the star formation rate in AGN from usual indicators. So, for example, Romange alpha luminosity, because the ionization source of AGN is not stars, so we have to find another indicator for star formation rate. And we have then, led by Rogério again, developed a method to calculate the star formation rate from the spectral synthesis. So we obtained the star formation rate from the mass that's going into the formation of stars until 20 mega years. We experimented with 10, 20, 30, but 20 was the good age to find a correlation between the star formation rate derived from the cell population with the star formation rate derived from page outreach. So this correlation was obtained from star forming regions in galaxies. AGN and non-AGN, but in the disc of galaxies. So this is why for star formation regions. And then we could find also obtained for this star formation region the star formation rate obtained from the cell population and from the correlation. So we can get a relation between the two, this relation. If you want the gas, you can get the size and vice versa. But the most useful thing is to use directly the star formation rate that we get from the cell population synthesis to study the how is the star formation rate in AGN versus control galaxies. So this was PhD thesis from Lara. Again, the same like I said, 300 AGN versus 500 control galaxies. isolated the inner kiloparsec approximately, and these are the star formation rate from this inner kiloparsec. So we see a difference, a shift in the star formation rate distribution. Actually, the circumstance of star formation rate. We see that the star formation rate in AGN is about 2 times the star formation rate in the galaxies. Okay, and then we obtained also the main sequence of star formation using the same methodology among the galaxies. So these are distribution for all the among the galaxies of the star formation rate as a function of the mass of the galaxy, and these are the main sequence of star formation. And relations from other by other people here, the main sequence of star formation. When we put our sample of 300 AGN and 500 total galaxies, we see that the AGN are at the main sequence and below the main sequence, but together with the clones, and this would be for the integrated, because this main sequence is for the integrated line of the galaxy. So even in the integrated line, the AGN show a bit of an excess of transformation rate relative to the control galaxies. So still the star formation in AGN, star formation rate in AGN is higher than the star formation rate of the control galaxies. So our conclusion is that the ongoing activity increases star formation, not quench the star formation, as Luis said also in the previous one, that the ongoing activity is related to an increase of star formation, not quench. And my explanation, as I said, is the same gas that's going into feed AGN is also forming stars like me, and also collaborating with Alejandra in the Emission Center to singular study. And she has a poster here in the conference. And can we find further signatures of star formation around surrounding AGN? And then I recall this work that I did in 2005, where in the spectrum, the nuclear spectrum of NGC 10 and 7, there was a galaxy that discovered a double-plated profile, transient double-plated profile. I found a Starburst in UV. So in order to UV, I had to put a Starburst, but I had to put a lot of weathering to reproduce the UV, indicating that there was a 1 per Starburst within my parcel from the supermassive black hole. And this reminds this idea that was also shown before in this conference that this would be a Starburst in the outskirts of the Torus, as proposed by Zihuagn and others that was presented by previous speakers. And that, because we have a very strongly webbed Starburst that would come from the outskirts of the Torus, and the scale more or less 9 parsecs, similar scale. And this also shown by Ismael, that I found also within the Gaussian spectroscopy star forming ring that is correlated with the molecular gas in the hot molecular gas. And almost finishing here is some preliminary work I'm doing with the narrow light superpoint spectra and the UV. These spectra are always below the accretion mix model, and it's hard to describe the accretion mix model. And I try to do a combination of random Starburst and random power law from the accretion mix, and I can reproduce better the slope. So this is just preliminary, suggesting that maybe you can see Starburst also in signature Starburst also in narrow light. And finally, the little red dots that also show this compact AGN in the first million years of the universe, and they are polemic, but everybody discusses what is the origin. Yeah, so they are, I agree that with the proposal that they are compact AGN, but they have a lot of star formation, because star formation can explain this upturn that they have in the rest frame spectra. The rest frame spectra are red, they also and blue UV. And we have been doing some experiments, and then for this part, pure spectra, we can reproduce the spectra with an accretion disk, a red accretion disk, and a very young starburst to reproduce the. So this is preliminary, and we are working on this. And these are my conclusions, so I leave there this issue. Thank you very much.
Thank you, guys. Very nice. We have some time for questions. So I saw this start aside.
Thank you, so I agree with your message. My only point is that if we take care about the interpretation, we are using AGN galaxies. In this case, the contribution of AGN will generate a bluer spectrum, and this bluer changing parameters in the spectrum will provide you a degeneration in the decomposition. It will be providing more different stellar populations and other populations similar to the Asian degeneration. But and okay, this is.
I'm having difficulty to understand you at the moment.
Okay.
What's your preparation?
Well, the question is also that need to take care about how to apply stellar populations in this when you are using AGN galaxies, because the contribution will produce in the decomposition of stellar populations more junior stellar populations that should not be by. That is not from the stars, it's from the AGN.
Yeah, you mean that the life in the AGN can make it difficult to separate, the young star formation. Yeah, we know this problem, but we have been working hard with that problem. I think we are secure that we are having a correct answer. Okay. And we are doing the optical and also in the near infrared, and we observe consistent results. For the intermediate age, for the youngest age, I like to look on further, as I showed that signatures, other signatures that is indeed star formation, but for you, but UV, I think, is the correct wavelength to look for the youngest stellar population. Thank you.
Thank you, Thaisa, for this nice overview. The second, you wisely warned that when you said that ongoing aging activity, instantaneously, capture aging velocity. Is related to enhanced.
It's related to enhanced formation, but not the AGN proposed. It's that,
This is the current status of the galaxy, which is, we know that aging is bigger, right? They're only us. So I think it's starting to be clear that to understand what AGN is something to the star formation is, we need something that is not the AGN of mass, but something that encapsulates a cumulative effect, which is the black hole issue, not the black hole issue rate of AGN of mass, the black hole mass. There's a different place.
So you think that the presence of the star formation enhanced separation is related to the maximum black hole?
So the current status, and this is instantaneous aging. It's not a cumulative feedback, this is a relevant thing. I mean, you look at the numerical simulations, they explore to what extent different parameters are relevant for star formation, and it's not aging. It's a black hole mass.
That's right.
Yeah, it encapsulates the whole history of different agents.
Thank you.
Thanks a lot. I have like a little follow-up question with that one that Hector asked. So you calibrate your self-commission rate calculation method, and if you could show the plot quickly, because it seems to me, I'm not sure I got it properly, but that there is a slight offset if that one is a one-to-one relation, and it seems that with the self-population, you are a little bit overestimating the self-population rate.
This was, I cannot read anymore. The volume of calculations are so good. Projects, all are for different samples, but it's from start from the regions in our sample, because the sample we studied this work was about 300 AGN and 500 total galaxies, and we look only at the starforming regions in these galaxies to find the calibration. So we calculate the star formation rate from the star formation and compare with the star formation rate we get from the gas indicator HR. So we found these relations. And depending on the sample, doesn't mean one is from the AGN and the other is from the contours, a little bit difference. And so, yeah. This one, I'm not sure now exactly is this, which one, this one. So you are that it's a bit offset the slides. It's for different samples, okay? So this should be the average, considering all the success.
So we have
I wanted to ask you any relation between geological properties, optical properties, and the properties of the EVN, and specifically the parameters that are related to the so-called vector one sequence, like for example, dominance or possibly emission.
It's an interesting question. This sample we didn't look much because these are low luminosity AGN, and very few have iron emission, very few are silver ones. So it's a small sample of silver ones and a larger sample of silver twos, but low luminosity. So we didn't look at this aspect of the iron vector one.
Thank you so much.
Our next speaker is José Maldonado, who is going to talk about monthly pHs, so monthly pH in Emission Galaxy, programming by Stellar Data.
Thank you so much to the organizers for giving me the chance to be here presenting my work. I'm José Portilla. I am a master's student at the Biological Observatory at the University of Rio de Janeiro. And today I'll be presenting the work that I've been doing in my master's with the help of my advisor, which is titled pH emission in galaxies, proving Astrochemistry with JWST. So I was very happy to hear more talks about pHs, like pHs. Okay, so we study light emission across different wavelengths. This provides different information into the galaxy composition, the structure, and the activity. But does not obscure these observations. So this is where pHs come in, as they're the extension of the interstellar grain size distribution into the molecular domain. As they said, observe UV ultraviolet radiation, and they limit it as infrared radiation. So AHs are polycyclic aromatic hydrocarbons, which are large carbon-based molecules. They're organic molecules with 6 atoms. They're found in the extracellular. They can be compact, condensed forms like colony, or have more open or regular configurations like berry. And their planar structure facilitates stacking or clustering them. And they can have modifications. The arrangement of the atoms around the AHs also influences their spectral features, how we perceive them. They can be dehydrogenated, superhydrogenated, or substituted with heteroatoms, different from carbon and hydrogen. They can be very diverse, and they serve as building blocks for other molecules, especially these emission from the sign up. And what we can see how from the single monomer of AHs, which is benzene, we can go all the way up to pyrene, but the pathways to get there are multiple. So in process in the path, we can get neutral AHs and also ionized AHs, which have different spectral features, so we can differentiate them. And these strong mid-infrared features work as tracing conditions, which make them ideal for studying both physical and chemical conditions in galactic environments. They're also sensitive to star formation and AGN radiation fields, so they have connecting chemistry with the astronomical observations, and we can study this to the mid-infrared spectrum. So before, to understand pHs, how they vary the environment, we especially resolve spectrum. And the best we could do was to study spectrum by whole galaxies through a single state spectra. That's where JWST's the IFU comes in to get spatial resolved data. And it covers the 5 to 3 microns, the region for the infrared, divided in 4 channels or 3 sub-channels, which it's the key regions for the AH studies, where we can get the bands that correspond to the vibrational modes, like the carbon-carbon stretch and the carbon-hydrogen in-plane bending and out-of-plane bending for each corresponding bands. And but to put all this into practice and build a pipeline that works as the foundation for our research, we first focused on Galaxy ABC 7469, producing JWST data from those, which was reduced with the JWST pipeline. But we chose this one because it's a low-infrared galaxy that contains the Zihuagn AGN at its nucleus, and it's started circularly around it, which makes it like the ideal laboratory for studying these variations in these radiation environments. And to put all this into practice, we extracted the spectral data clips. We decided to go with the spatial resolved data. We decided to go with concentric annular regions to study how pH features vary as a function of distance from the nucleus to the galaxy towards the outskirts. So already from just extracting in different regions, we can see that in the inner annular regions, we get higher contribution from the continuum, and as we move outside, we get more defined pH features. And we can see that this pH intensity is also vary with the rate of distance. Also, we get information like the atomic lines that indicate AGN, like ionized and sulfur, which was mentioned before, can end up resulting in the reduction of pH abundance or complication of its diversity, which we'll show later. And we get the different slices of the concentric annular regions for each of the subchannels. We then station together to get a continuous spectrum. And then we use, well, for spectral composition, we use the 2 pH weight, which lets us separate the contribution from the continuum to well, atomic lengths and most importantly the pH features. So it's as if the pH weight tool lets us peel off the contribution. It lets us see the deeper information that we care about, just as in the Shawshank Redemption. We have the Rita Hayward poster that once built let the protagonists see the deeper reality beyond the region. So we do this spectral composition for each of the rings that we have, 8 rings, which runs as the isolated pH features for their subclasses identification. And once we have these for each of the rings, we use the NASA AGN-fueled spectral database to compare with our observational data, so that we can classify these pHs that we have into families to differentiate them by size and by charge states. Okay, so what we got for now is that closer to the nucleus of the galaxy, we have a higher abundance of neutral pHs, and these decreases as we go outside, and the same the opposite happens for the ionized pHs. So we start with low contribution of ionized pHs, and as we go outside of the nucleus, they increase. And in regards to the size of compounds, different found that there's a bigger contribution of smaller pHs when we go towards the nucleus, the galaxy. So what we were expecting was that with the harsher radiation of the AGN, we would get more ionized pHs, but from our results, it seems like there are other evolutionary effects that are taking place. So in our research group, we're exploring the scenario of dehydrogenation and fragmentation being slightly favored, energetically favored in X-ray radiation over ionization. Also in our group, we have found, in other works, we have found the same trend in bigger samples, where we also get more neutral and smaller pHs where the AGNs are strongest. So pHs end up reaching new chemistry and astronomy into astrochemistry. They absorb the liquid radiation, we get as infrared, lets us study chemical and physical conditions of galaxies. Thanks to JWST spatial result spectra, we can map these and study different regions, using molecular chemistry to the environments. And what we got that in the harshest AGN environments, pHs go toward the more compact and neutral forms. Thank you very much. And my recommendation is the estimate work, especially snail, which was published in 1993, but also like way before. It just didn't even come to publish it. And it's about a community banding together to fight for like the greater good. It's my favorite movie, but it also reminds me of how us scientists went together and to reach the deeper understanding of the universe.
So we have time for some questions.
Comment is that, of course, the neutral pH is defined also in the parallel velocity would just be in the shielded area in this. So my question related to this is that you did this analysis in rings. Do you actually have enough signal from noise to actually do the essentially pixel? And to see if you see any position angle dependence or how it relates to the geometry of the AGN?
So we should be what
if you could not do this analysis in rings, but you actually do it by pixel in the cube. So you look for every pixel, how is the ratio of these different pH types, and then see if this relates in some way to the geometry of the AGN.
You're suggesting that I should use by this instead of constantly rings.
This is a suggestion, but it depends if you have enough signal to noise. So, would it be possible?
Yes, we decided to go with the concentric regions to get like a broader siding how the pH takes differently sort of like that.
A comment on the question. So, with the case of Q, it's very difficult to go faster because you have no impedance. This is because the PSX is not super well sampled. So, to that work, I see that the group will give a paper on 7.59 as well faster. And then you get a for release in the papers.
So, very much you go as we go on the PE spectrum. Yes.
Any more questions? Stephen?
You say that in favor that neutral hash, neutral pHs in AGNs. And you say there's more. I thought that I would launch the AGNs one. Can you comment on that?
Yes, we're just really excited with these results, but in our group, we haven't found this in any other works. I have here work from a colleague on my group that she was using feature iris data, so not spatial result, but she had a sample of about 615 galaxies. And she also found that a lot more neutral and more small pHs contribution. Maybe it's about how small are we talking about the pHs? And that's what but yes, we were also surprised with this results.
Looking at the DFT decomposition, right? So, we have some composition on the vertical spectrum used by this one. So, this database is complex, and one of the things that I'm not taking into account harmonic effects, because the system is very so I usually how to get the size of this field or all of them. The size that you derive from this field is okay. So I see that this is a little bit tricky because of the. The other thing I would like to ask you is to let me say something about the generated ones. But this one should be much more the 6.2% the 60 pounds. Yeah, you go the next slide, maybe.
No, this is all
For the conclusion, I think that we have.
Yes, so you say that the electric one could be the one explaining the data, but they are using mostly the system. Well, we can start. We have another. Okay, this one's Herrera. So our next speaker, the speaker of the session is Giorgia Peluso, who is going to talk about AGN-fueled enrichment in the process for
hello guys, I am Giorgia Peluso. I am a postdoc working at the University of Bologna, and in this session today I want to show you this work about the gas phase and the chemistry of AGN, and in particular the role of the rampage splitting. So let's start with a very general introduction about this topic by saying that the gas mechanism of AGN is measured in previous works, but discrepant results have been found. Indeed, some works find that the nuclear regions of AGN hosts are less enriched than those that suffering Galaxies, while other works find basically the opposite result, which is that AGN are more enriched than suffering Galaxies. So, the first result could be explained by a strong AGN feedback that advances with some formation in regards to nuclear regions and melting mineral production. While the second result could be explained by many hypotheses, among which, for example, the gas extraction or comparing star formation, and so on and so forth. One of the questions here is how this relationship changes across different environments, and in particular, today I will focus on the cluster environment where the rampage splitting is occurs. For who is not super familiar with it, the rampage splitting is the pressure exerted by the positive medium on the colder interstellar medium when a galaxy falls into a cluster. So this is like a wind blowing through the galaxy and creating this kind of one-sided gas. And the most extreme cases are called jellyfish, which have stays even longer than the galaxy within itself. As you can understand, this process is capable to deeply and profoundly alter the properties and the matrix of the gas basically throughout the entire galaxy. And some calculations investigated the interplay between the rampage splitting and activity. In particular, this work, Riccardo 2020, simulated two galaxies falling into a cluster. One without supermassive black hole, which is the red curve, and one without a supermassive black hole, which is the blue curve. And in particular, they predict that after the intensity peak of the rampage splitting, which happens around this peak of, both the star formation rate and the specific molecular pressure rate increase, especially the specific molecular rate is increased drastically, which is actually in alignment with observations, as we observe that jellyfish galaxies have both enhanced the star formation rate and the activity with respect to main sequence, let's say, normal galaxies. So one of the questions here was if AGN hosted by AGN, like jellyfish galaxies, can have a different mechanistic distribution with respect to AGN triggered priority mechanisms, such as, for example, stellar bars or mergers and so on and so forth. Also, another interesting result of this work is that the star formation rate decrease much more rapidly in the galaxy with a supermassive black hole rather than the galaxy without the supermassive black hole. So the authors interpret this result by saying that the AGN feedback can distribute the gas in the inner regions in the galaxy, and then this gas can be more easily split by the pressure. So basically the synergy between feedback, and microsweeping can avoid the galaxy gas more rapidly. So under this assumption, under this scenario, we would expect stripped AGN to be less enriched than non-stripped AGN, because stopping the formation earlier and also stopping the production and evolution as well. So to investigate all of this, we select a sample of ground-specific galaxies from the Galaxies survey. Galaxy is the acronym for Galaxy Phenomenon Galaxies, and is a national program, the spectral news. And basically the goal of this study was to study how, when, and why the gases are moved from galaxies, and what is the interplay between the gas physical conditions and the activity of the central black hole. So to do so, the program examined 113 galaxies located in different environments, so clusters, filaments, or groups. The majority of them were in clusters, and these are not in the Emission network. So these galaxies are pretty massive and are located at low redshift, meaning that the spatial resolution is nearly 1 kiloparsec. Here you can see some examples of galaxies observed by GASP, and in particular in white, you can see the stars, which are basically really undisturbed, while the gas distribution in these galaxies is highly disturbed, which is indeed a clear sign of ongoing pressure sweeping. So among those galaxies showing clear signs of pressure sweeping, we identify 11 AGN according to the diagrams. 6 are secret, while 5 are liners, but the liner galaxies also have an atmospheric source, overlapping with the optical center, consistent with the AGN activity. We also wanted a control sample of galaxies with similar properties than the pressure sweeping sample, but unaffected by environmental effects. So we use the manga survey and we select the subatomic galaxies, so with a high specificity information rate, later type morphology, but located in a low mass scale, which means that we consider them to be located in the field, and so presumably not experiencing any pressure sweeping. To spot the AGN among these galaxies, the criterion was to classify the emission, which is your sample of the galaxy center, and to state if the ionization is mainly due basically to the stars or to an AGN. So here you can see one example inside the galaxy of this outside these galaxies were considered were classified as AGN in the DPT, and so we classify the galaxies. To measure the metallicity, we use an indirect method, and we both number task aurora lines are faint to apply the method. So we produce the ionization models using the cloudy, and in particular, in this model, with the ionization center or emission lines, assuming the ionization from AGN, from stars, or from a mixing component. And we used and we focus on particular on these 2 line ratios, the oxygen over sulfur and nitrogen over sulfur, because as you can see, coupled together, they break very well the degeneracy between the ionization parameter and metallicity. And also in this case, the models were not well with the observations, which are the Pascal points. And this is important because we also use the coordinate database to compare models and observations, to constrain the ionization parameter and mechanicity inside each pixel of a galaxy. And at the end, we obtain this mechanicity max with the mechanicity gradient. Also, the use of the code of the Crowley model scattered on a molecular base is a very, in general, is a very computational expensive technique. So we obtain 3 equations that express the mechanicity from cloudy as a very simple combination of the observed oxidative sulfur and sulfur ratios. We publish the calibrators in the paper that that you can see scanning the paper code. These are very cheap and very easy to use, and one is for the geo regions, for main regions, and for the compost regions specified by the PPT. So you can use to measure the mechanism and analysis of energy and using a consistent assumptions in regions united by different mechanisms. Check out the paper because you can find everything that you need to do that. So we find that the agent costs, which are the three points here, follow mass consideration similar to stuff from Galaxies, but this is weak, presumably because the stellar mass range spanned by the Galaxies limited, as the region are also followed by the more massive galaxies with up to 10 solar mass. We find that on average, AGN lie above the mass metallicity relation, also forming galaxies, and even regardless from the galaxy environment, in the sense that we don't see a statistical significance difference. The only two exceptions are these two galaxies, which are jellyfish, and they have phase, they have metallicity lower than subatomic galaxies at basically any ranges. At this stage of the analysis, 2 out of 11 agents, we consider them as outliers because we didn't have enough statistics, basically. But these highlight how much larger sample of non-precious galaxies also the integral spectroscopy are actually required to investigate this kind of threat. We do observe, however, that the meta-enhancement is linked to the central AGN activity because AGN costs have higher meta-density at any given range than subatomic galaxies, but the steepness of the gradients increase only in the very inner regions, so we need to concept. And broadly speaking, actually, AGN shows super solar metallicity and very high metallicity at basically any redshift, from redshift 7 up to the very universe, according to many books, so many books of this. This points toward the enrichment of the gas. JWST is now able to perform better and replicate this kind of process. And so, hopefully, in the future, we will be able to investigate and replicate this process. And with this, I will give you my summary and I will take questions.
Thank you so much, Giorgia, for this nice talk. We have some time for questions. Yes, thanks.
Nice talk. Let me ask you. So, which year is your interpretation for the higher capacity in the AGN? You know, where the excess of the systems?
I would like to explore more the hypothesis of the dust destruction in general. I think that these may be one possible pathway in the sense that in the early regions, stuff with previous workbooks, and the pure addition of the gens is capable to dissociate these dust grains. We also observe generally bigger grains in the gen vicinity, meaning that smaller grains are destroyed. And of course, these grains contain metals. So if they are destroyed, they can enrich the gas with metals. So I think that this needs to be parts.
Let's ask.
My brand is an designer, it's amazing watching designer without subtitles, but no, sorry, with subtitles. Sorry, it's very much.
Thank you all for being this last session of everything happening.
Just a reminder that the opportunity is another in the last Sirena Bola this afternoon for dinner.